Hi, my name is Lucas Equeter. Thank you for watching our contribution that is related to the maintenance of cutting tools. The maintenance of cutting inserts is a costly activity. This is due to the low mean uptime of cutting edges, which must be replaced every 15 to 30 minutes. Given the costs of these inserts and this short uptime, the question one should permanently ask is whether the cutting inserts may continue machining or whether it is best to replace it. Yearly, billions of dollars are at stake in the US economy alone. The cause of these losses comes from early or late replacements. A simplified vision of this dilemma may be stated like this. An early replacement is a loss of a fine tool, whereas a late replacement induces scraps. In the industrial practice, the replacement is based on several possible factors. The worker's experience on the basis of the machining noise or the personal assessment of the machine surface quality, the machining time since last replacement, and finally, the more modern option, tool condition monitoring. Each of these options corresponds to a type of maintenance. Obviously, the first case is highly dependent on subjectivity, and it is unclear how one should qualify this option. Then we have scheduled maintenance or condition-based maintenance. That is the current industrial practice, so let's have a look at the standard guidelines. In turning, for example, ISO 3685 defines conditions for tool life testing. These conditions are based on the flank wear of the tool, when the average measurement of the flank wear in zone B, denoted VB index B, reaches 0.3 millimeters, the tool is considered to have reached its end of life. The second condition is met when the maximum measurement of the flank wear reaches 0.6 millimeters, and the end of life is decided upon whichever comes first. Now, in comparison with the industrial practice, it may be linked to two of the options. The scheduled maintenance option is directly derived from the standardized option. On the other hand, in the framework of condition monitoring, one may try to identify, through the use of sensors, the moment when this criterion is met. However, the limit of 0.3 millimeters is arbitrary and it does not correspond to any industrial optimum, hence the search for a remaining useful life estimate which focuses on an industrial optimum. With this respect, one should establish clear industrial objective, among which the foremost criterion is likely cost-related, but it is likely correlated with other criteria, more physical criteria, such as the tool wear. Once the KPIs are identified, then statistical methods allow to estimate a RUL with respect to the industrial objectives. To sum up, what do we know so far? Well, we have our process data, the duration of machining cycles, the number of machined workpieces, the costs, etc. We also know what we would like to optimize, be it the cost or the scrap rate, for example. In turn, we would like to be able to use a maintenance policy that best satisfies these demands. So, for cutting tools, what do we need to invent between both in order to make it from one end to the other? First off, let's acknowledge our maintenance optimization criteria. What do I want to optimize? Most likely the answer will be the cost or the profits. It may also be the quality in a zero scrap policy. But let's go for the cost for a moment for the sake of the example. It may be broken down to some of its components: the new tool cost, including handling and assembly, the worn tool handling and recycling cost, the unavailability of the machine, and the scraps. All these correspond to the total of costs over the lifetime of a single cutting insert. Obviously, one would compute the asymptotic average cost over time or over the whole life cycles. We can obviously refine a bit depending on whether the tool failed and induced scrap or whether it was replaced preventively. The computation of costs therefore depends on what scrap is, what tolerances are necessary, and how they are checked. And this brings us to the question of condition monitoring. Indeed, depending on the tolerances of the machine surface, the condition monitoring variables may be chosen accordingly. Usual suspects are the cutting forces, vibratory measurements, offline flank wear measurements, etc. The real complexity of this part is strictly to identify the variables that indicate the imminence of a failure. This is strictly case-by-case research with help of the literature. The most probable way to go is the identification of the tool failure mode, which induces scrap, and deduce from it the condition monitoring variables that would best be correlated. Short point before continuing, this entire step may be bypassed if the condition monitoring variables are well known or if the tool failure probability distribution parameters are so well known that they make condition monitoring a waste of time and money. I personally doubt it, but it may happen. What's left? Writing down the actual replacement policy. Now come the subtleties. Machining is not a continuous operation, and it cannot be stopped about any time for a maintenance action. Unless a catastrophic failure occurs, one waits for the end of a cycle before replacing the tool. This is why the computation of the remaining useful life by itself is not sufficient. But it should, on the contrary, be compared with the duration of the next cycle, which is known, obviously, thanks to the G-code. If we want to put that in terms of probability, we actually are trying to compute the probability of no failure occurring until time t plus cycle duration, knowing the current state of the tool at time t. But let's stick with the RUL estimate for now. We'll break down the case into two possibilities depending on the bypassing of the previous step, that is, without condition monitoring or with condition monitoring. Without condition monitoring, the strategy will be to rely on statistical distributions of the failure time and to best identify their parameters. The failure time is strictly defined as the time at which the tool is no longer able to produce within the tolerances. It is more convenient to use the actual duration of the contact between the tool and the material rather than a number of cycles that may vary from one workpiece to the other. In consequence, once one determined the reliability distributions, the failure will still occur for a fraction kf of the tools, while the preventive maintenance will replace tools that did not fail yet for the rest of cases kp. In this case, the remaining variable to choose is kf, which must be optimized with respect to cost. Reducing kf to 0 would lead to an infinite cost, but the scrap costs make a failure more costly than preventive maintenance, so an optimum may be found. What if we're using condition monitoring then? It's more complex, but possibly more rewarding. The tool wear may be considered as the best option for describing the evolution of the tool life, but it's necessarily an offline procedure that is time-consuming and necessitates image post-processing. Fortunately, a large range of wear estimation methods were developed in order to assess the tool state at a time given other condition monitoring variables' values. Condition-based maintenance may be used by factoring in the value measured in condition monitoring variables. As an example, one would trigger the replacement of the tool once the cutting forces reach a certain value. Final option, my favorite, predictive maintenance. If, in addition to all of the above, one can estimate the influence that the planned following machining cycle will have on the tool, then we can estimate whether the next cycle will bring the tool to fail, and if so, we can replace it beforehand. Stochastic models or survival analysis, for example, may be used for this. In each case, with and without condition monitoring, we now know when to replace a tool. So let's have a look at the industrial implementation of this methodology. Let's imagine I'm trying to get from the subjective calls of the worker to using this methodology. First thing, collect data, minimum, the replacement time, and the cause of the replacement. Second, explore the potential gains without condition monitoring through simple statistical analysis. Third, if that works, see what investment would be necessary to do some condition monitoring on the variables that are most related to the failure modes. Why am I precising this? Because Industry 4.0 will bring big data to our computers, but correlation is not causality, and the actual physical relationship between variables must be privileged. Fourth step and foremost, once the maintenance policy is defined, challenge it on the basis of experience and loop the method as much as necessary. A lot of variables are involved. The variability of cutting tools, of materials, will influence a great deal of these policies' results. The constancy of the supply chain for both materials and tools must be assessed. The definition of tolerances should be kept to the functional, no need to over-specify. They also must be unequivocal in order to make the definition of acceptable workpieces identical and common to maintenance and production personnel alike. Finally, other tools such as total productive maintenance should not be overlooked. They may play an important role in the improvement of quality and cost reducing. What I presented today is not per se a new approach in maintenance. On the contrary, it is common practice for most maintenance policies. Yet, cutting tools are late on this one, but they are also costly. And this is why the first objective must be to clearly determine with all involved parties the optimization objectives, usually cost-related, and what workpiece is acceptable or unacceptable. Then, the tool replacement must occur close to, but before scrap is produced. At the dawn of Industry 4.0, we must keep the physical sense of the data analysis. I would like now to thank you, and I will gladly answer to your questions.